Hi, today we're gonna study free fall in AP Physics 1. When you look down a well or over a cliff, you may be tempted to drop something to see how far down it will fall. You're instinctively trying to use kinematics to determine the distance to the ground. The method you're using to investigate the drop is the focus of this lesson, and it's called free fall. In this lesson, we'll apply our knowledge of kinematics to free-falling objects. The study of falling object dates back to ancient time. In the 3rd century BCE, Aristotle claimed that the speed of falling object depends on its mass. In other words, heavier objects fall faster. In 1589 CE, Galileo argued the contrary. He said that the speed of a falling object does not depend on its mass. So, who was right? According to the Aristotle, the heavier objects should hit the ground first. This means heavier is they represent light. Heavier objects first. Galileo said that two objects hit at the same time. Same time. Let's find out by dropping two objects of differing mass from the same height. When you research videos concerning the free fall, you can see that Galileo was correct. Is it what you expected? It turns out that the speed of falling object is independent of mass. But if this is true, then why does a falling feather or a leaf from the tree seem to disobey this rule? During the Apollo 15 mission to the moon, astronauts demonstrated that a feather will fall at the same rate as a wrench in the absence of atmosphere. So, strictly speaking, Galileo is only correct if the object are dropped in a vacuum. That is, if they are dropped in an environment with no atmosphere. Practically speaking, objects do behave in this way on Earth as long as there is no significant air resistance. The study of falling object is a special case of one-dimensional motion called free fall. Free fall is the acceleration of an object due solely to gravity. On the surface of the Earth, acceleration due to gravity is a fixed constant, given by the symbol g, and measured to be a vector with magnitude of 9.81 meters per second squared, pointed toward the center of the Earth. To describe free fall motion, we'll use the same equation we have already found for one-dimensional kinematics, applying some standard convention often used when dealing with free fall. For an object traveling in the vertical direction, as is the case here, the axis is taken to be perpendicular to Earth's surface and pointing away from Earth is in the positive directions. So the acceleration of an object in free fall is minus g, which indicates the object is accelerating towards the Earth, minus g. We can rewrite the equation of motion for an object according to this convention, substituting minus g for a. The short equation becomes v equals v initial minus 3t. The long equation is y equals y initial plus v initial t minus 1/2 gt squared. Or delta y equals v initial t minus 1/2 gt squared. Recall delta y equals y minus y initial. The combined equation is v squared equals v initial squared minus 2z times y minus y initial, or v squared equals v initial squared minus 2g delta y. Now let's imagine that we are standing on an unknown planet. What basic tools could we use to determine the gravity of that planet? Time is a fundamental quantity that is easily measured with a stopwatch. We'll pretend like we have one of those with us. Distance is also an easily measured quantity if we have a measuring tape. Let's use our stopwatch and tape measure to design an experiment that will determine the gravity on an unknown planet. We'll start with what we know, kinematics. The kinematics equations for free fall describe the motion of a falling object. Therefore, our experiment should probably examine the motion of falling object, noting the distance it falls and the time it takes to hit the ground. We'll let those be our given. Climb a 50-meter high cliff and drop a log to the ground below, measuring the fall time to be 5.19 seconds. Our unknown is the gravitational acceleration of the planet. Okay. Now that we have our givens and an unknown, let's try to solve the problem. The height delta y equals 50 meters. The fall time is t equals 5.19 seconds. G sub planet is what we are looking for. Are there any other givens we may have missed? Let's take a moment to consider all aspects of the scenario. What other given quantity might we know? We drop the object from the rest. That means we know that the initial velocity is 0. We can add v initial equals 0 meters per second to our list of givens. Let's list our equation and begin solving the problem. Which of our free fall kinematic equations can best help us determine the gravitational acceleration g? V equals v initial minus ut, or delta y equals v initial t minus 1/2 gt squared, or v squared equals v initial squared minus 2z delta y. Note that if all of those vectors y, v, and g are pointing down, then it makes more sense to define the downward direction as positive. Then the equation looks like this. V equals v initial plus gt. Delta y equals v initial t plus 1/2 gt squared. V squared equals v initial squared plus 2g delta y. Notice that the second equation has all the terms we know except g. Let's use the one. Delta y equals v initial t plus 1/2 gt squared. Letting v initial equals 0, we get delta y equals 1/2 gt squared. Solving for g, we get g equals 2 delta y divided by t squared. Turns out our unknown planet is actually worse, with a gravitational acceleration of 3.7 meters per second squared. Now, let's review that we covered in this lesson. We will learn that the kinematic equations apply to free-fall motion, but that they require special consideration for the vertical frame of reference. We also learned that all objects fall at the same speed in a vacuum. That's it for this lesson. I'll catch you guys in another video. Thank you for watching.